Welcome to StatsCast. The purpose of this series is to explain statistical concepts in a way that is clear and simple, even if you don't have any previous experience with stats. This video explains the purpose of t-tests, how they work, and when to use them. In another set of videos, I'll show you how to use and interpret t-tests on some popular software programs. So what does a t-test do? It's very simple. A t-test checks if the averages, or means, of two groups are reliably different. That's all it does. Now you may ask, well, why not just look at the means? Looking at the means may tell us if there's any difference at all, but that doesn't tell us if the difference is reliable. For example, if you and I both flip a coin 100 times, and you get heads 52 times, and I get heads 49 times, does that mean you reliably get more heads than me? Are you somehow more likely to get heads in the future? No. There's no real difference, it's only chance. This leads us to the difference between descriptive and inferential statistics. A descriptive statistic only describes the sample we have. It doesn't tell us if our results are likely to happen again. In contrast, a t-test is what we call an inferential statistic. Inferential statistics don't just describe our sample, they tell us what we can expect in new samples that we don't even have. Inferential statistics allow us to generalize our findings to a whole population beyond the sample that we're testing. That can be very powerful. Let's take an example. Researchers have developed a new drug they hope will lower cholesterol. Let's call it t-testrol. They take two groups of people and give the drug to one group for a month. That's the treatment condition. The other group gets an empty pill. That's the control or placebo condition. After that month has gone by, the researchers measure cholesterol for both groups. They find that the control group, which didn't receive the drug, now has a mean cholesterol score of 36. The treatment group, which did receive the drug, now has a mean cholesterol score of 34. Descriptively, these two means are different. But does the drug actually work, or was this just chance? Would a similar result happen again with a new sample? That's why we need inferential and not just descriptive stats. The t-test will tell us how likely this difference is to be reliable, or whether it's just due to chance. Well, how does the t-test do this? How does it work? Well, I won't go into the full formula, but basically it measures the difference between the groups and compares it to the difference within the groups. The t-value is just a ratio of these two numbers. Variance between groups over variance within groups. A t-value of 3 means your two groups are about 3 times as different from each other as they are within each other. That also means that if groups have wider, more scattered scores, it will be harder to detect a real difference between the groups than if they had narrow, tightly clustered scores. You can think of it as a signal-to-noise ratio. The signal, that's the difference, is easier to detect when there's less noise. That's the scatter. In our example with the cholesterol drug, the difference between groups is about 2, while the difference within the groups is about 6. 2 over 6 gives us a t-value of 1/3, which is not big enough to be reliable. Based on these results, we can't say the drug actually helps lower cholesterol. But how do we know if it's big enough? Each t-value has a corresponding p-value. The p-value is the probability that the pattern produced by our data could be produced by random data. In other words, it tells us whether the difference between our groups is real, or if it's just a fluke. So, a p-value of 0.05 means there's only a 5% chance we would get these results with random data. A p-value of 0.01 means there's only a 1% chance we would get these results with random data, while 0.1 means there's a 10% chance. In most research, the cutoff for what we consider reliable, or statistically significant, is a p-value of 0.05 or below. Now, the exact p-value associated with a t-value depends on how many people are in your sample. Bigger samples make it easier to find statistically significant differences. For example, with two groups of 5, a t-value of 2 has a p-value of 0.04. When you increase the sample size to two groups of 10, that same t-value of 2 now has a p-value of 0.03. Bigger samples are helpful, but the benefit diminishes as the sample size increases. A good guideline is to try and have at least 20 to 30 data points in each group. If your sample is too small, you may not have the statistical power to detect differences that really are there. Sample size is represented through a number called the degrees of freedom. For t-tests, the df is the sample size minus 1. There are three main types of t-test: the independent samples, the paired samples, and the one-sample test. The most common type is the independent samples t-test. This is when you have two different groups you want to compare. Our cholesterol experiment is an example of this type of test. Let's take another example. T-tests were first developed in the early 1900s to check for differences in quality in batches of Guinness beer. That's another example of an independent samples t-test. If you need to test two different groups, this is the test you need. Just to make things confusing, there are a few different names. Other than independent samples t-test, they're also called between samples or unpaired samples t-tests. However, they all mean the same thing. Another type of t-test is the paired samples t-test. This is when we have one group that is measured at two different times. For example, we could test the quality control team at Guinness and test their balance before and after they test their batches of beer. In a paired samples t-test, each score is paired with another score, usually because the measurements come from the same subject. This is different from an independent samples t-test, where scores between groups are not related. This pairing gives us more statistical power as it reduces possible variability between subjects. However, it's also susceptible to ordering effects. Again, paired samples t-tests have a few different names. They're also called within subjects, repeated measures, or dependent samples t-tests. Again, it all means the same thing. The last type of t-test is the one-sample t-test. This is when we only have one group and we want to compare it to a hypothetical value or a known population mean. For example, the mean IQ is 100. You could test if your coworker's average IQ differs from that by using a one-sample t-test. Like most stats, there are some limitations that go with t-tests. First, you can only generalize to a population that resembles your sample. If our cholesterol experiment was only tested on adults, we can't rightfully say the results also apply to children. Second, your sample and population should be roughly normal in their distribution. This means the scores resemble a bell curve around the mean. If the distribution is skewed, your p-values may be inaccurate. Thankfully, t-tests can handle a fair amount of departure from normality before they start to break down. Third, you should have close to the same number of scores in each group. Comparing a large group to a small group can lead to inaccurate results. Fourth, your data points should be independent of each other. That means the outcome on one score should not influence the outcome on another score. Fifth, your data should be at least interval level or close to it. This means that one unit of your score is equal to any other unit. If you're using ranks, like first, second, third, your results may be inaccurate. If your data is unruly and breaks some of these rules, you do have a few options. You can do a Monte Carlo simulation to test whether it is safe to use the t-test. You can also use another kind of test instead, like a Mann-Whitney U-test. They can take more abuse, but statistically they're less powerful. Finally, let's go over how to read and write a t-test. Let's go back to our cholesterol example. Styles may vary, but this is a typical way you may see t-tests presented. First, the name of the test is given. Then, each of the statistical values. The t-value tells us the size of the difference, and the p-value tells us if this is reliable. If the p-value is less than 0.05, then the difference is considered reliable, or statistically significant. The number in parentheses is the degrees of freedom, which is the sample size minus 1. Here, since the df is 99, that tells us there were 100 people in the sample. Finally, the mean scores of each group are given. In this case, there was no significant difference. But if there was a significant difference, this is how we would write it out. When you have a significant difference, the means are especially important, as they show the reader which group is bigger. Well, that's all for this video. In future StatsCast videos, we'll learn how to do t-tests using a computer. Bye for now, and happy computing.